Hi, I'm Jiaqi Chen, a recent PhD graduate from Hansen Research Group at Florida State University. Today, I'm excited to introduce one of our latest publications, Increasing Excited State Lifetimes of Copper-1 Coordination Complexes via Strategic Surface Binding, published at Inorganic Chemistry Frontiers. When there is external stimuli like light, the molecules will go from its ground state to its lowest synchronized excited state, and then it will happen a structure distortion and then relax to its ground state. This kind of structure distortion will have lowest energy of the state, minimize the energy of the transition excited state, and also decreases the reactivity and reduce energy gap. And then it will limit its application like in catalysis, lighting, and solar energy conversion. This happens in all the molecules, but especially in transition metal coordination complexes. Nowadays, people use a lot of elements like ruthenium, osmium, and iridium as desensitizer, but they are very expensive and rare. So people want to use the first row transition metals like copper to replace ruthenium. However, is a pseudo-John-Taylor distortion happens during the excited states of the copper complexes. So when it is copper-1 and it's at ground state, it's a 4-coordinated tetrahedral-like D2D structure. And when you shine the light to it and lose electron, it will have a torsion to flat it. It will go from this D2D structure to a square planar D2 structure, and which will open a site for the solvents to attack, and which will shorten its lifetime. So in order to inhibit this kind of distortion during the copper excited states, people use several methods. The most popular one is this direct substitution. So this is a phenanthrene. So people usually put bulky groups at 2-9 positions. For example, if you put methyl group at 2-9 position, you will go from no emission to have about 90 nanoseconds in DCM. And for now, the most successful one, they already reached about 2.8 microseconds in the DCM. However, this kind of method will lose the rigidity of the molecules, and it will also slow the electron transfer rates. A few ways that can inhibit distortion is you can interlock it with superstructures and well it make a crystal. However, it's very difficult to design the kind of superstructures, and the crystal will limit the interfacial contact. So compared to the previous steric bulky groups, what we proposed is using a surface binding strategy. What we do is we bind it to be more specific. So when the more copper complexes is in the solution, it will be easy to distort. And we will have this kind of entering groups. For example, here is carboxyl group. Bind them to the metal oxide surface. By binding to metal oxide surface, we hope it will inhibit distortion of it. In order to study surface binding strategy, we used these two complexes as our study series. So for the molecule 1, we can see the entering group is at the metal position, and because it's at the metal position, only one of the ligand can be bind to the surface, and the other side will be still easily distorted in the solution. And for the complex 2, we can see the carboxyl S group is next to the methyl group, and because of this kind of structure, both of the ligands can be bind to the surface, which can further inhibit distortion of the molecule. So first, we need to bind them to the surface. So we loaded them to the surface by soaking a zirconia dioxide film in the methanol solution, and then we can see when it's on the top is when it is in the solution. We can see the strong ML safety band near 500 nanometers, and when it is binding to the surface, we can see the strong MLCT band at the 400 to 600 nanometers as well, which indicates the molecules are successfully binding to the surface. And we can see the surface binding will have like a minimal impact of this kind of protonation states. We can see for the powder samples, we can see it has a strong peak at around 1700 as well as the 1200, and both are the carbon oxide stretching peaks. And when it's binding to surface, we can see the decrease of both peaks, which indicates it's binding to the surface. So to study the excited states, we use transit absorption spectroscopy. So one is solution sample and the other one is surface sample. So by soaking it to the zirconia dioxide surface, we make it a sandwich style like structure. So we have our loaded sample, we put another glass on the top, and we use a syringe to infuse the methanol solution to our sandwich structure, and then we seal it with another piece of glasses. And then you will be able to mimic the solution environment. And we started on the transition absorption spectroscopy. So by exciting the molecules at 500 nanometers, we can see when it is in the solution, it has the excited state absorption above 650 nanometers and the ground state bleach below the 600. And when it's binding to the surface, we can also see the excited state absorption features above the 600 and the ground state bleach as well. So we fit them into the single function for the solvent solution and also the bi-exponential function for the surface sample. So we can see when it is in the solution, this molecule 1, which is only one of the carboxylic acid group combined surface, it only have a lifetime at about like 80 picoseconds. But when it's binding to surface, the lifetime is increasing to 640 picoseconds. So this is about like 8 times increases when just binding one of each to the solution. And for the molecule 2, which is both of the molecules can bind to the surface, so we can see when it is in solution, it has the excited state absorption above 550, and then the ground state bleach below 550. And when we is bind to the surface, we can also see the excited state absorption feature above 550 and the ground state bleach as well. So we can see for the molecule 2, for the complex 2, at the early time scales, which is below the 30 picoseconds, there is a slightly blue shift of the excited state absorption, and this is often attributed to the vibration cooling. And this small blue shift occurs about like 500 picoseconds for the surface solution. So when this is in the solution, we can see the lifetime is about 90 picoseconds. And when it's binding to the surface, the lifetime is increasing to 1960 picoseconds. And by binding both of the molecules on surface, there is about like 22 times changes of the lifetime. So if we put them into the same figure, we can see when binding to the surface, they both have dramatic life changes compared to the solutions. They both have like longer lifetimes. And when both of the molecules can bind to the surface, it has a much longer lifetime than only one of them. However, methanol is known as quenching the lifetime in solvents. So in order to study solvent effect, we use the ester version of these two molecules to study the solvent influences of the molecules, because the ester version will have a better. In order to study the solvent effects, we loaded both of the molecules on the PMMA. So when it is on the PMMA, there is no solvent can attack to the molecules, which should not have any solvent effect of the molecules. So we can see for the complex 1, which is only one of the ligands combined to the surface. When it is a solution, it's about 80 picoseconds lifetime. And when it's loaded to the surface, it has 640 picosecond lifetime. And when it's on the PMMA, it's about 2560 picoseconds lifetime. And similar to number 2, when both of the ligands combine to the surface, when it's in solution, it's 90 picoseconds. When binding to the surface, the lifetime increases to 1960 picoseconds, and when loaded on PMA, the lifetime is increased to 1600 picoseconds. So we can see for number 1, when it's binding to the surface, it reaches about like 25% lifetime as it is loaded on PMMA with no solvent effect. But for number 2, when both of binding it can reach actually 43% of the lifetime on the PMA, which there is no solvent effect. So we can see when it is sulfur binding, it can actually reduce the solvent effect of the complex. In order to further study the solvent quenching of the copper complexes, we use the ester versions in methanol solution and the chloroform solution, and also the solid samples in methanol environment and chloroform environment as well. So we can see for the molecule 1, when only one of them can bind the surface, in the methanol, the lifetime is about 70 picoseconds, and in chloroform, it increases to 2660 picoseconds. And when the number 1 is in the surface, in methanol, the lifetime is 640 picoseconds, and in chloroform, it goes up to 2420 picoseconds. And when both of them bind the surface, in the solution, in methanol, the lifetime is about 55 picoseconds, and then in chloroform, it goes up to 2640 picoseconds. But when it's binding the surface, both in methanol and chloroform, the lifetime is similar. When it is methanol, it's about 1960 picoseconds, and when it is chloroform, it's 1660 picoseconds. So we can see in the solution environment, the lifetime is about like 40-fold increases from the methanol to chloroform, which we think is because of like absent the excited state quenching when it is in the chloroform solution. And we can see when it's loading to the surface, the solvent effect for the complex 2 is much less significant, which indicates when both binding to the surface, it can help inhibit the distortion, which will have less solvent effect. In order to further study the complexes, we use the DFT calculations to optimize the geometries of compound 1 and 2, and in their like singlet, ground, and lowest energy triplet state. So we can see in this figure, the ground state molecule orbital diagrams is shown. So we can see both the molecules, they exhibit ligand-based lumos and copper-based homos. And also the homo 4 can be described as primary metal-centered 3D orbitals. When we did the calculation, we used the interligand dihedral angle as the evaluate method to study the degrees of planarization between the ground and lowest energy triplet MLCT state. So this is angle between the planes of the bipyridine ligand, and also since it is not like the perfect D2D geometry, there are two ways to measure it. So when it is 90 degrees, it is a tetrahedral structure, and when it is a square planar structure, the degree should be around like 0 or 180. So we also could calculate the differences, which is the 90 degrees minus the degree, which will provide information on the from tetrahedral conformation. So we can see on this table, for 1 and 2, we all see the flattened from its singlet to its triplet state. And when we see the complex 2, the changes is about 9 degrees, but for number 1, the number 1 complexes, the changes is only about 2 degrees. So we can see the flattened structure going from singlet to the triplet state, and we can see because both of them can bind to the surface, it can help distort the molecular distortion to the square planar geometry. In order to further study the structure of the molecules related to the surface, we use the polarized ATR as a powerful means to determine the durations of the molecular transition dipole moments. So we have the results concluded in the table 4. So we can see for the molecule 1, the tilting angle is about 47 degrees. And for the complex 2, when both of them combine to the surface, it exhibits a tilting angle of 62 degrees. So compared to the one that only one of them bind to the surface, the tilting angle is larger. So based on our experimental and theoretical results, we have this kind of figure, proposed structure of the complex 1 and 2 related to the dipole moments related to the metal oxide surface. And also combined with the ATR-IR results, we can see the results is consistent with that only one of the ligands of 1 can bind to the surface, and for 2, both of them can bind to the surface to inhibit the tetrahedral to square planar distortion. So for the conclusion, we use a new strategy, surface binding, to inhibit distortion of corporate complexes. So we have this kind of 2 different complexes with the binding groups at different positions, and with the picoseconds transit absorption spectroscopy, we studied the excited state dynamics of both molecules, and we combined with the PAT polarized ATR as well as the computational analysis to support the structures and how it can inhibit distortions on the surface. Thank you for everyone's attention. If you are interested in similar research like this, please follow us on Twitter or Instagram at HansenFSU. Thank you.